Now we're going to look at another problem in electrostatics that not only exemplifies a few key concepts of electrostatics problems, but also allows us to begin practicing with one of the most, I think, the most useful tools in the study of electrostatics, which is Gauss's law. All right, so let's get started. Now, this problem may seem a bit contrived, but it will prove to be useful. What we are given is a large spherical volume. A large insulating sphere with a uniform charge density is how that this would be presented. Within this sphere, there is a very thin hole that is drilled all the way through. Now I'm drawing it with quite a large diameter in the hole that's been drilled just for the sake of illustrating this. But the reason that this problem would say that this is a very small hole and a very large volume is to convey the idea that the process of drilling this hole would remove negligible material. So the effect of having this hole drilled through the middle of this sphere does not in any way affect its overall charge. So you can think of it as almost an imaginary tunnel drilled through this sphere just for the purpose of the rest of the problem. The reason that this hole is drilled, so I'm going to put a few things here. We're going to have a center of our sphere, and we're going to have a radius of this sphere, which is capital A. And then the reason that there's a hole drilled through is so that there can be placed two small independent charges. You could think of these as very small charged beads. You could think of them as small charged particles, whatever is helpful for the concept to you. And they are free to move in that hole. There are no friction forces at play. They're not going to experience any friction, and we're completely neglecting any external forces like gravity or external fields or anything like that. So what we are considering today is simply what is drawn on the board. All right, so both of those small charged particles have a independent charge Q. Now I'm going to label this as Q1 and this is Q2 just for the sake of our analysis. And then the overall charge of the large sphere is capital Q. And this would be the information that we would begin with. All right. So we need ourselves a roadmap. What is in question here is that when this system is set up, eventually these two charged particles will come to an equilibrium position. The equilibrium position implies a few things. Equilibrium implies that they are not moving in time or in space, so they are static. And since they are free to move and not held in place, this must mean that there are forces holding them in place. If you look at just Q1, if it's going to be in an equilibrium position, then there must be a force in this direction and an equal and opposite one in this direction so that it does not move. So there will be forces at play. Now let's draw our distances. So what we are asked to find here is the distance d. Now I have not drawn this perfectly, but d is the same for both. So these charges being identical, these charged particles, Q1 and Q2, they'll have identical distances from the center of this sphere. We want to find what is the length d. We want to find a formula for the length d. Okay, now if we were to take away this larger sphere and just only consider Q1 and Q2. Since they are identical, now we don't know if they're negatively charged, we don't know that they're positively charged, they're one of the two. But since they're the same, like forces or like charges always repel each other. That means that this Q1 will experience a force going to the left because of the field of Q2. And it will be the exact same for Q2. It will experience a force going to the right due to the field of Q1. Okay, when we bring the larger sphere back into play and have everything just like it's set up here, because these are at equilibrium, we can assume then that the opposing force due to Q of the larger sphere is going to be in the opposite direction on both of these particles in order to hold them in place. All right, so what's our roadmap? We want D. We want to know what is D. That is what's in question here. If we could find formulas for the forces, if we're just, let's say we're going to analyze Q1, if we could write down the forces to the left being equal to the forces on the right, then as long as those forces are written with respect to D, then we might be able to solve for D. So we need then to find the force. If we can find the forces, that will lead us to D. Well, in electrostatics, how do you find a force? The force is due to an electric field. Okay? F equals Q times E, where E is an electric field. Let's see, as we go forward, let's look only at Q1. Everything will be exactly the same, the math and the concepts, all the same for Q2, so we only need think about Q1. And there are going to be, of course, two forces as we've drawn. We're going to have the force on Q1 due to Q2, so I'm going to write that as FQ1, Q2. There will also be a force on Q1 due to effectively the larger charge Q, capital Q. In electrostatics, the Coulomb force is the force due to a small independent charge. Let's see, maybe that's not the best way to write this. All right. So let's think about this force. Let's think about the force on Q1 that is because of Q2. Q1, and then we must have some electric field from Q2. Now, we know from Coulomb's law exactly what this electric field is. We can write this as Q2 over 4 pi epsilon naught, and then the distance r between, or the distance r away from the source Q2 squared. Now I've written it as r because r is not the same as d. Now r is the distance away from the source in which you want to evaluate the field. That's the total distance between Q1 and Q2. So r squared here, actually I'll write r. R is equal to twice d, and if we square both sides, then we get that r squared is the same as 4 times d squared. And so that can be replaced here, 4d squared. This is then our electric force, the magnitude of our electric force. I have dropped effectively the vector component here. It would be in the radial distance between the two. So if you were to draw a straight line from this charge to this one, that would be the vector direction of this force. We can, if we want, simply say what is the magnitude of this force, and because r is a unit vector, then we could say that the force on Q1 by Q2, its magnitude, so no vector, is equal simply to Q1, Q2 over 4 pi epsilon naught 4d squared. All right, so that's one step. We're good. Let's write this down up here so we have more room on our board. FQ1 because of Q2, magnitude is equal to Q1, Q2 over 4 pi epsilon naught 4d squared. Okay, so we're one step further. We have one of the two forces that are acting on Q1. All right, so now we wrote directly the force due to the electric field of Q2 acting on Q1. Now let's see what does the electric field do because of Q, larger Q. All right, this is where we shall employ the use of Gauss's law. Gauss's law is a very helpful tool for electrostatics. Gauss's law says that the surface integral over an imaginary surface, this is just a tool that you can use so that if you have uniform charge, you can draw a spherical surface, if it's helpful, at any point within that distribution to evaluate the field at the surface of that imaginary Gaussian sphere. Okay, so we have then that the surface integral of some electric field at its surface, dA, is equal to the charge enclosed by that imaginary surface over epsilon naught. Now, epsilon naught is simply a constant. It's the electrical permittivity of free space, and will be given to you, or you can look it up. It's not something that we actually have to solve for. All right, let's see if we can make this integral a little more tractable. If you think about an evenly distributed volume charge creating a constant electric field inside a sphere, its field lines radiate in all directions out from the center. So then I could rewrite E as the magnitude E times its unit direction vector r hat. R hat represents the spherically symmetric radial vector that emanates out in all directions equally. So I can rewrite then this as E r hat. Now what about dA? dA vector is a way to represent a small infinitesimal surface patch or little surface area in a vector fashion. A surface vector is always represented by its normal, which is perpendicular to the little surface, and for a sphere it is in the same direction as our field lines, emanates out in all directions equally. So we can then write dA vector as magnitude dA times r hat. If we then plug these into here, replacing them, we would have something like this. We would have integral, surface integral, E dA magnitude, and then r hat dot r hat. But what do we know about two vectors dot product with each other, and they're in the same direction? Their dot product then is just the multiplication of their magnitudes. In unit vectors, their magnitude is 1. So this actually just becomes 1. All right, so this makes this look a lot better. E dA, no vectors necessary. Now E is constant because we have a uniform electric charge density inside our volume. So E comes outside the integral. We now have a surface integral over a sphere, which equals the surface area 4 pi r squared. I've left this as r because it's not a. So this r is different than a. This r represents the radius of our Gaussian surface. The Gaussian surface is drawn inside the larger sphere, at its surface being at the same radius as the distance from the charges from the center. So this r is actually going to be d. 4 pi d squared times e. Now what about this q enclosed? Q enclosed is the amount of charge that is within this Gaussian surface. So how can we calculate that? A charge, a total charge, is the same as multiplying its charge density by the volume in question. So if we could find the charge density, multiply it by that inner volume, then we would have Q enclosed. Now charge density, it's not blatantly obvious, but we actually can calculate it. It is in a manner given to us by the problem. It's the same as our overall charge by the outer volume, the larger volume in our diagram. So this would be Q, which is given to us, over 4/3 pi a cubed. All right, so we have tau, and we know V inner. So tau is Q over 4/3 pi a cubed. We also have then to multiply this by the inner volume, which is 4/3 pi d cubed. Perfect. And we simplify. 4/3 and pi both go away. And we write then that E times 4 pi d squared is equal to 1 over epsilon naught Q over A3 times d cubed. All right, now we're getting somewhere. This is good. This is very, very good. This is an algebraic equation very easily rearranged to solve for E. So we're going to write the magnitude of the electric field at the point Q1 due to Q enclosed. It's just a label. That's just the way we're labeling it. Nothing magical about that. E is equal to 1 over 4 pi epsilon naught times Q times D. Now we have, we're at D because if we divide both sides by D squared, there's only one factor of D left over, and that is all over A cubed. This then is our electric field. So we can go from electric field and then to force. We want to know the force on Q1 due to Q enclosed. Its magnitude equals Q1, the charge in question, multiplied by E, this EQ1Q. All right. Now Q1 QD over 4 pi epsilon naught A cubed. All right, now that's what we like to see. One note here that you might run into and have some question about, depending on the book that you use or that your professor is using or which class you're in or how you're studying electrostatics, you might see let's see, I'm going to use Coulomb's law just to demonstrate this. You might see something like the force is equal to Q1 Q2 over 4 pi epsilon naught R squared. All right, so there's Coulomb's law. You might see it written like this with epsilon naught, or you might see it written as KE Q1 Q2 over R squared. These are equivalent. All it says is that this constant KE is equal to 1 over 4 pi epsilon naught. This is an identity. KE equals 1 over 4 pi epsilon naught. It simply depends on who's doing the teaching of which you will see. I usually write in terms of epsilon naught, so we're going to leave it that way today. Okay, so we've got our forces. This is our first force, this is our second force. Let's get us some room. Let's write that F, force on Q1 due to Q, is equal to Q1 QD over 4 pi epsilon naught A cubed. Now, if we set these equal and opposite to each other, and the reason that we can do that is the problem states that these charges are in equilibrium. Equilibrium meaning forces acting, if there are forces present, there must be equal forces in opposite directions, keeping that particle stationary. So if we set these two equal to each other, we have that Q1, Q2 over 4 pi epsilon naught 4d squared is equal to q1 qd over 4 pi epsilon naught a cubed. All right, let's do some cancellation. 4 pi. And we have then simplified q2 over 4d squared equals qd over a cubed. Now we're trying to solve for d, so we're going to rearrange this slightly. And we'll have that d cubed is equal to q2a cubed over 4q. All right, I think that is correct. Yes. And then if we take the 1/3 power of both sides of this equation, which we are allowed to do, we solve for d, and it is equal to q2 over 4q, the 1/3 power times a. All right. And there you have it. There's our solution. If for some reason or somehow someone ever does an experiment taking a large insulating sphere of uniform charge density, drills a small tiny hole through it with 2 charged particles in it, then you should be able to measure, at least close, that the distance that they settle from the center is equal to this. All right. Best of luck.